talk about this. Okay, so let's. So I actually forgot about something I was going to do. So and thanks to Mahmoud for asking another question. So I threw something here for you guys. Intro to simulation, right? 1102. So you know, I kind of talked about this in a big hurry earlier when some of you didn't know what a pseudo-random number was. So let me just quickly get you right into Apache Spark on how to simulate. So the core idea is, you know, it's called the Monte Carlo method, and there are lots of tales about why it's called Monte Carlo. And one sort of tale is that when Ulam and von Neumann were in Los Alamos working on these problems with the nuclear detonation, whatever they were doing, they will get stuck in pure maths, and then they will use this trick to get some insights. You know, they'll use pseudo-random numbers. But supposedly, almost every time they would get stuck, I think his Ulam's uncle will show up, and he's this gambling addict who just kind of freaks out. And so I think I don't know, he came to get money, maybe. So anyway, it was this internal joke. So we codenamed, I suppose we codenamed it as Monte Carlo because this guy, this gambling addicted uncle of Ulam would supposedly show up. I have no idea if this is true, but that's what I was told by a professor at Cornell who wrote a book and stuff. Okay. So anyway, this is also called Monte Carlo method. So the main idea is this. We have numbers from 0 to m, and then we do modular arithmetic, modulo m. And then if certain arithmetic operations in this, it's a discrete dynamical system. You start at some number in 0m, and then you land back in some other number between 0 and m. If that pattern looks completely indistinguishable from a truly uniformly sampled sequence from 0, 1, then we say it's pseudo-random. And then what you do is just divide it by m and get rational numbers between 0 and 1, okay, excluding 1. And then you pretend that these are samples from the uniform 0, 1 random variable. Okay, that's the idea. This is now a continuous random variable, and m is so large, so it doesn't matter, right? So now once you have samples from the uniform 0, 1 random variable, then there are lots of ways to transform them into samples from other random variables or random vectors or random networks or random walks on random networks or interacting agents, models. Everything comes from this, okay? So it's just the simulation levels, the transformations get more and more complex, but under the hood, it's just these things. Okay, so we will, of course, not have time to go into all of this. However, we will revisit this when we get into Spark's GraphX, the graph processing distributed vertex programming library. So we will do a lot of simulated random networks to play with. So this is the uniform distribution. This is called the probability density function, okay? And this is uniform 0, you know, when A is 0 and B is 1, we have the uniform 0, 1 continuous density. And then this is the distribution function. So it simply comes from taking the density and integrating it all the way from -infinity to the point of interest, right? So that's that. And when you integrate a straight line, you get a slope. That's all the CDF is, right? So that's capital F of x, and this is lowercase f of x. So of course, there's a lot more than just the probability density function, the cumulative density function, the cumulative distribution function. There is, of course, the mean, which is the expectation, the median, the point along the density, such that the probability to the left of it is 0, and the probability to the right, sorry, is half, and the right is half. That's the median, and so on. Okay, so let's not get overly carried away. Now, let me say that there are sort of two simple starting points to get, you know, to get the uniform samples from a uniform 0, 1 random variable transformed into the others. We will come to this method. It's called the inverse transform sampling method, and in a minute, concretely. The other one is called rejection sampling. This is sometimes also called the fundamental theorem of simulation. Right? This idea is also due to von Neumann. So here is so the idea in rejection sampling is just that we let's see if this is, yeah, this is too complicated. Okay, so basically the idea is that we have so we have some complicated density. Let's say this is the density, probability density function, something super wiggly, let's say. Now what I can do is, maybe just put a little triangle on top of it, okay? Some other density basically, or it doesn't have to be some other function. That's called the envelope function, right? It's guaranteed to be above the density of interest at every point, okay? So let's say you put a little tent literally on top of it. Now what we can do is we can produce samples uniformly at random from this tent-shaped thing that encloses the density, right? Just put the tent on the ground, so now you just have a two-dimensional, polygon, right? And then what you want to do is spread points uniformly at random on this polygon, right? To do that, there's many ways, right? I can chop it into little rectangles and find the areas of them, and then take my uniform pseudo-random numbers, and then put a certain weight of them according to these rectangles, and throw away the points that land outside the polygon, right? So then I can get my uniformly distributed points on the polygon. Now what I do is I go back and say, okay, let me put where the density is on this thing as well, and then throw away all the points that land above the density, right? So that's called rejection sampling. I reject it. Now all the other points that are sitting there left, as they were, now you just sort of turn the thing up and drop them to the ground. They're samples from the density of interest, right? This is a very, very powerful idea due to von Neumann. It's called the fundamental theorem of simulation, because all you need is you have the target density, you have to envelope it with something else, and you choose the envelope in a shape that's easy to produce uniform samples from it. Simply throw away things that land above the density. So, okay, so those, and with these two things, you can basically sample, transform uniform 0, 1 to anything. Now, with Breeze stats distribution is how we're going to, this is the linear, linear algebra maths package for Scala. So here is another slightly more interesting density, the Poisson distribution, right? So it's this has a parameter called lambda. It's mean parameter, and when lambda is 1, this is the probability mass function. Because the Poisson distribution is discrete, it's not continuous. Instead of having a probability density function, you have a probability mass function. So it tells you where the masses fall. And this just gives you the probability mass of falling at 4, falling at 5. And so when lambda is 1, there's a much higher probability that the Poisson distributed random variable, say capital X, takes the value k with a very high probability close to 0 and 1. Okay. And then if lambda is 4, you see there's more probability of the random variable taking a value close to 4, and so on. So this is just a parameter, and this is just the cumulative distribution function. So I basically take, this is really a whole bunch of needles stacked here at each point. So and then I integrate it, which means it's continuous until there is a jump, and then it jumps like a staircase, right? That's what this is now. So this is the cumulative distribution function for the Poisson. And okay, so now let's just get our hands dirty. So this is, I import Breeze stats distribution, and then I create my immutable poi as new Poisson with rate mean parameter 0.3. So now just a black box, completely, let's draw 5 samples. Black box. Okay, we don't know exactly how it's doing it. But it's somehow transforming pseudo-random streams into Poisson, right? So let's just take it like that. And then this gives me my sample of 5 samples drawn at random from Poisson distribution with rate 3, or sorry, mean 3, right? Because the poi is fixed. So if I try this again, so I got 3, 2, 2, 3, 2. If I try it again, I get 4, 2, 2, 4, 2. So it's like, because the seed for this is changed every time. It's probably taking from the milliseconds clock or something. So that's sort of the idea. So now conceptually, you can just actualize or have realizations from this Poisson distribution. Okay. So now we also often are interested in getting the probability. So this is the probability mass function, right, of the Poisson. So I'm simply taking x, in my S is just the sample. So 14806 is what's in memory. And I'm simply doing, give me the probability of x using this method for the object point, which is the Poisson with mean 3. Yeah. Okay. So now sometimes you may want to cast this into a double because x is actually integer valued because the samples are integers, right? So you may want to just cast into a double so you can do it this way, for example. Yield x dot to double. And then now I'm just asking the Breeze stats mean and variance of this double poi thing, because I just want this to be, now I'm taking 1,000 samples, right? So that gives me my mean is 3.001 and my variance is 2.85 and my in the sample is 1,000. So now let's look at the Poisson distribution and see what is its mean. So its mean is lambda. So the mean parameter is how this distribution is controlled. And look, the variance is also lambda. So Poisson is special because its mean is its variance, right? So anyway, and then these things are quite close to 3. So we know this seems sensible, right? And so if I do maybe 10,000 and it's going to get closer to 3, right? Let's just see. Waste some electricity in Oregon. Okay, so there you go. It gets closer to 3. Okay, maybe don't put like too many zeros, right? Oh, I might cry. Okay. All right, so then I'm just now computing the population mean and variance as well. So this is just, it just comes from the actual expression, right? So that's just this thing. So we know from just, it's just evaluating lambda. Okay, so now let's look at exponential random variable. This guy is actually quite cute because if you have say buses arriving or some particles arriving in continuous time with this such that the time between arrivals is this exponential random variable. So let's look at the density function. This is how the exponential random variable. So its expression is lambda e to the minus lambda times x. So when lambda is 1, it's lambda e to the minus lambda x is 1 at 0, and then it just decays exponentially at rate 1. And of course, when lambda is 0.5, it starts here and goes slower, and if it's 1.5, it starts here and dies faster. Of course, the area under this curve is the probability, and it should always be 1 by axioms, Kolmogorov's axioms of probability. So that's why they kind of have to. Okay, so fit around. So then this is the CDF. So I'm integrating now a continuous density from 0 to infinity, and so as I increase, it's going to be, as I go to the right, it's going to be sort of blowing up like this. So that's my CDF. Here are my expressions for Pdf and Cdf. Lambda e to the minus lambda x. 1 minus e to the minus lambda x is the CDF when you integrate this guy from minus infinity to x. Okay, and median and so on. Median is 1 over lambda log 2. What else? That's good. So then the other thing I want to pay attention to later is the inverse distribution function. Okay, let's get into this in a sec. So this is my this is how I instantiate my exponential random variable with rate half. So I'll call it expo. So expo dot rate is half. It's the rate parameter. Now I'm simply remember log 2 times the rate basically is where the median is. So if I evaluate the probability at the median, I should get half, right? So then I'm I'm evaluating the probability from 0 to the median, so that should be half, right? And also, if I do the same, Control C, so let's make sure all of this is mathematically sensible. So if I do this, right, so if I do some really big number, that should be also close to half, okay? That's the median. Right, this should technically be infinity, right? In Sage, you can do all that. In Sage Math, you can actually do all that properly symbolically if you want. Okay, so here is export or probability. So if I want just what's the probability between 0 and 1.5, I'm integrating the density, right, from 0 to 1.5. So that's almost 95% of the probability is between 0 and 1.5. Because the mean is just 0.5 in this case. It captures quite a lot. Okay, so I don't know, 1.5 times 0.5 is 0.75 for some reason. I don't know why I did this. No idea. Okay, so, oh yeah, so this is just the CDF, right? Just CDF of the exponential. Now let's just go here, right? Now I want to start drawing samples. I said let's kind of do it a little bit less black boxy, right? So if I have samples from the uniform 0-1 random variable, my CDF for the exponential, if I invert the CDF of the exponential, so this is the CDF of the exponential, 1 minus e to the minus lambda x. So then what I really am interested in is inverting it. So this is the CDF. So if I have samples in uniform 0-1, then I have a mechanism to invert it and go back to the x-axis from the y-axis, then I'm done. I have this inverse CDF method, right? I can simply use it. So all I need to do is invert the CDF of the exponential. So the inversion basically is -1 over lambda, natural logarithm of 1 minus y, right? So y is my points in the 0-1. This is a samples from the uniform, okay? So this is powerful, right? Imagine, if this CDF, right, is going to be differently shaped, right? If my, if my lambda is very small, this CDF is going to get really spiky quickly, and then it'll go like this, no? Because what will that do? That'll move a lot of these points very, very close. They'll make them drop much closer to this 0, right? So the CDF really controls how you map little, little intervals in the 0-1 downstairs. That's basically, and it works for all densities in one dimension. Of course, it's not trivial to find the inverse mapping, right? For all densities, right? You need to have an expression for it. That's a whole industry, right? How to do this. Okay, so this is the black box way. We just say expo.sample2, and we sort it, and then we find two points, sample randomly, pseudo-randomly, and sort it. And then I'm simply just evaluating what's the probability from the first sample, or the smallest sample, to the second sample, which is larger. Just to show you some stuff on the same thing. I can ask for the mean and variance of these samples. So this is actually just the sample mean and the sample variance. And so what is the mean and the variance of the exponential random variable? Who knows this? By heart.
Versus B.
Yeah, good. Yeah, so the mean should be 1 over lambda. Yeah. And the variance is 1 over lambda squared. Okay. So it's unlike the Poisson, the variance is not the same as the mean. And so I think that's just a little sanity check. So 1 over lambda. So 1 over 2 is... Yeah. Yeah, so I think this might be the mean parameter, probably. Yeah. There's two ways to parameterize it. So yeah, so it looks like expo dot, no, sorry, what did,
The lambda is half.
the lambda is half here, right? Okay, good. I was getting confused because there's another way to parameterize, by the way, in some packages, and that's the mean. Yeah, so here the lambda is half, so yeah, 1 over 1/2 will be 2, so we should get close to 2. Okay, good. This is good. And this is 1 over, it should be close to 4, 1 over 2 squared. Okay, so yeah, I think, yeah, sorry, that's what I did here, right? Okay, good. So now, finally, let's start doing pseudo-random numbers in Spark, and how do we actually do this rolling our own, okay? So I have Spark implicits and SQL functions imported. Now I'm going to just create a data frame called spark.range1000 at the ID column, right? So if I'm not doing anything here, so let me just df.show 5. So it should be 1, 2, 3, 4, 5. And of course I have 0 to 4. And I have 0 to 4,999 or 999. So now I'm going to take that data frame. I'm going to, select this ID, but I'm also doing this little operation, right? I'm saying, give me rand. So this is the built-in random number generator. It'll produce uniform 0, 1 samples. I'm controlling the seed to be something. You can change it to whatever number you like. I'll just do 1, 2, 3, 4, 5, 6 just for fun. And then this is going to simply add a column of zeros and ones called rand. So if I just df.show. Okay, so now crucially, if I change this to say 1, 1, some other number, this is going to change, right? So you see, they're different numbers, different sequence of numbers. But the beauty is this, the beauty is if I go back and remove these, right? This is what I had before, 1, 2, 3, 4, 5, 6, 7. I reevaluate it. And, if I show it, this should be the same as before. So by controlling the seed, it's completely deterministic. So you can actually start doing debugging and things like this, right? So it's important to, but often like different pseudo-random streams can get mixed up if you don't know what you're doing, and then that's crazy. Here is all I'm doing now is just the same as before, but now I have a column called ONE adding. So this is literal 1.0 doubles. I'm adding a new column of ones, and I'm also adding a new column called rate, which is literal 0.5. Right? Okay, there's a slightly sexier way to do this, but I want it to be mechanical. This is what's going to happen under the hood anyway. Okay. So now I do df rand. I call this guy df rand. I said df rand show. Now I just have a whole column of ones, a whole column of 0.5. Right. This will work when you're working, when you want to scale the terabytes. Right. This is really what is really going to be going on. So now what I'm going to do is, why did I do this? I did this because I peeked into my little Wikipedia thing, and I know that the inverse distribution of exponential is -1 over lambda, natural logarithm of 1 minus the uniform sample. So I know I have to do a division involving constant 1, and also there is a same constant 1. Subtraction is okay, and then I have to do, this lambda. I need the lambda, the rate parameter. That's why I put the column of just ones and the rate lambda everywhere. So then that's it. So the last thing will I just do with column, and I just do expo sample. It's my new column I'm going to add, and this is my expression. So here I'm doing column operations, right? So it'll do this. This is completely, narrow transformations, right? Because all the information is in the row for the arithmetic I need. So there's no shuffling, there's no need traffic. So that's all that is, right? So this is how this is simply samples from the exponential random variable. Okay? So Let's see, if you don't believe me, if I don't believe myself, let's just make sure that we do display this guy, Control V, and then start just doing some histogram thingamajig and plot options, expose sample, see values. And what do I do? So let's see, what should I do here? Bar chart. Oh, sorry, I want histogram maybe. Yeah. So doesn't matter. Okay, so I have my histogram, so maybe I should increase the bin size to be a bit bigger, not too big. That looks nice. Okay, so that looks like samples from the exponential, right? Exponential with mean around 2. Okay, so this seems like very trivial maybe, but this is all you really need at the end of the day. So now, in more complex situations, you just will be playing with a similar idea. You'll have a column of pseudo-random numbers, maybe multiple columns of pseudo-random numbers if you need more entropy, but then you'll just use that to do your transformations. And if you have so one thing I've been doing with this Twitter analysis of US, UK, and now New Zealand elections, we're also monitoring eventually Swedish as well. So what we are usually doing are hypothesis tests, and in our hypothesis tests, we're often interested in the fact that are certain populations of interest who may be potentially violating law, are they actually doing something to the rest of the population? In the sense of, are there preferential retweets of these populations of interest by the general public that also preferentially retweets, say, one of the political candidates, for example. So that gives us some idea of some kind of, some kind of ideological concurrence, right, at a high level. But then if you want to turn that into a statistical hypothesis test and do a very formal p-value and all of this, you will usually have a null hypothesis you're trying to reject, right? And often the null hypothesis in this case would be, something like what we call apathetic retweeting model, right? So this is a model from statistical physics, network science. It's called the configuration model. So this model says people who retweet others or get retweeted by others, so you have arrows going in the direction of retweet, there is actually the total number of outgoing edges and incoming edges is constant. This is the same as what I observed in the empirical network. So if you preserve the total number of incoming and outgoing edges, right, then you have what's called a sample from the configuration model for that empirical network. So you take the empirical network, you look at every node's in and out degree, the number of incoming edges and outgoing edges, which basically means how many people retweeted your original tweets and how many original tweets of others did you retweet, okay? Then you take this and then you say, I'm going to completely randomize who I retweet and who retweets me, but I'll preserve the total number of incoming and outgoing edges. That becomes the configuration model. Of course, you need to sample from realizations of the configuration model, right? That's now instead of an exponential random variable, you now have a realization of arrows coming in and out, preserving the in and out degrees. And it's almost exactly the same. There's literally 3 more columns. And if your representation is just, from node and to node, you represent an edge by just a column of nodes, then you just do something very similar. You have a pseudo-random stream, and you do some random permutations of them, and then boom, the function takes this, and then it pops a realization of the configuration model. And then you do that, say, at 10,000 times, then you may have a test statistic, right, that you're measuring, and you want to know if that test statistic, the null distribution of that test statistic is somehow what it is, and then what is the observed test statistic, and compare it with the null distribution, right? That's the standard generalization of Fisher's tests. Does this I think the scientists should understand this, right? This is Monte Carlo p-value sampling and null distribution, and do you guys all know this? Okay, good. So that's where you can do, right? Okay, now we're really running on time. So we did this already. So let's get into linear algebra, right? So a little bit more prep work. What do we have here? So this is basically Breeze. 12 minutes. So I'm going to stop the streaming and we're going to watch Amit's video now, okay? And then we'll come back to Scala from next week.